This is think, my alternative to solid. If you're expecting another acronym with a bunch of made-up rules, good news, you're in the wrong place. I'm Gábor Szabó, I teach .NET, I write code, and I've been in this field long enough to know when something's more cargo cult than substance. And I think it's time we had a real conversation about solid, what it gets wrong, why people still cling to it, and what we could do better instead. So, solid. You can't even code properly, yet you're introduced to solid right after learning the word class. The ideas go back to a 2000 paper by Robert C. Martin, aka Uncle Bob. You probably know him, loud opinions, high output, big influence. He doubled down in his 2002 book, and after that, solid took off. Also worth noting, same guy authored Agile, clean code, and pushed UML. A lot of what some people teach today as the right way. The acronym SOLID itself, that came later. It's branding. Let's not pretend it wasn't. What nobody ever talks about is that SOLID is just one set of principles from that paper. There were two others, package architecture and package coupling. But those didn't get a catchy name, and surprise, they didn't get famous. We don't teach RCC or ADP in boot camps. We'll also get back to them later, but I wonder if you can spot why. So, ask yourself, was SOLID really the most valuable set, or just the most marketable? Look at this. This is the Agile Manifesto, straight from the original site, like today. Looks deep, right? Individuals and interactions over processes and tools. But just take a step back. These aren't engineering principles. They're bumper stickers. They feel profound, but just try applying them in the real world. No structure, no context, no fallback plan. That's exactly the problem with how solid is usually taught, like gospel, not guidance. Sure, you can elaborate on them all. Solid, agile, clean code, these were made into books. But it's not science. No academic structure, no mathematical foundations, just semi-structured thoughts. Even with this in mind, the problems run much deeper with solid. So let's get into it. We'll go through each principle, what it claims, how it's usually interpreted, and where I think it falls apart if it does. Then, we'll zoom out and talk about the bigger issue. What happens when you treat these 5 ideas like some holy rulebook? And finally, I'll show you my take. It's not an acronym. It's not doctrine, just a way to think. Let's be honest, this is what happens in a lot of teams. We teach solid, we expect better code, people follow it blindly, and somehow things get worse. Not because they're dumb, but because the rules, the way they're taught, leave no room for judgment. That's the problem I'm trying to solve. The single responsibility principle states a class should have one and only one reason to change. Sounds nice, but what does it mean? Doesn't even state the word responsibility. If you look at the paper, it's not there either. Responsibility is attributed to stakeholders in this example, not the code. If you look under the blankets, Uncle Bob later, in 2014, clarifies that responsibility actually means reason to change. I'm here to tell you that this is obviously categorically false. Did the definition change in his mind in the years in between? What counts as a responsibility? What if I have a class that has more? Am I, from that point onwards, simply a bad person? What counts as a reason to change? Who decides? It's vague, It sounds scientific, but it's not. I'm not saying it's not elaborated on in his book or his posts. I'm saying this is how solid is being taught today, without any context or critical thinking. And the moment you try to apply it strictly, you start splitting things that don't need splitting, or worse, you wrap everything in interfaces just to look clean. He also tries to offer another wording for the SRP. Quote, gather together the things that change for the same reasons. Separate those things that change for different reasons. End quote. These are not even the same definition, not even similar. Let's look at this classic solid example on the left. Everything's abstracted. Saver, emailer, logger, all injected, everyone has their responsibility. On the right, all in one class. Now here's the thing. Both are valid. But the solid version is prematurely abstracted. It adds complexity before it adds value. And the worst part, that email sender takes an invoice. Does that mean it knows about invoices? So who's violating SRP now? The processor or the email sender? Or its interface? This is the problem. Once you start breaking apart code based on a feeling, it turtles all the way down. Next is the open-closed principle. Sounds nice. You should be able to extend the class's behavior without modifying it. This principle basically says, or at least upon further examination in the paper implies, inheritance is good, switch is bad. Okay, but which behavior? What if the thing I need to extend was never designed to be extended? What if changing it is the simplest, safest thing to do? And even that's a false choice. Sometimes switch is simply the best tool you've got. Here's a textbook OCP setup. You want to calculate totals and you abstract out a discount strategy. Now your logic lives in a separate class. It's interchangeable, reusable. But let's be real, you added a lot of ceremony. And it only helps if your discount logic is going to change in multiple ways. Otherwise, it's just more surface area to maintain. Plus, even VIP discount strategy hardcodes a 0.9 factor. Should that be abstracted too? Should the multiplication, the conditional? Where does it end? The counter example. Clean, simple. But is it extendable? Well, if you said no, you would be totally wrong. Can't you just edit the code? Maybe you can. Specifically, in this example, if you're given this task at work, the code, maybe not in 2000, but nowadays, code evolves. It doesn't just stay the same. And if you need a part of the logic interchangeable, you'll make it so. It's as simple as that. You'll arrive at a solution that's like the one on the left. Not because you applied OCP, but because it's natural. Otherwise, just go with the one on the right. Now this one's different. Liskov actually defined this formally. It's not hand-wavy. The Liskov substitution principle states if a class inherits another, you should be able to use it as if it were the base. But you know, modern OO languages, you can't even pass an integer to a method that expects a service instance. It won't compile. But this is different. Derived classes must be substitutable for their base classes, semantically, not just syntactically. Most violations happen when a subclass pretends to be a base class, but changes the meaning of its behavior. Like, if you inherit ellipse, but overrides its geometry to behave like a circle. Now, you broke the model. Now you can't move the two different focal points of a circle because a circle doesn't have two focal points, even though it is an ellipse. I offer you to look at the paper. It suggests a quote-unquote solution to the problem that itself violates both LSP and OCP. Next, this is a classic example. You've got a bird base class with a fly method, and then someone adds a penguin. Now what? Penguins can't fly? Do you throw? Do you know up? Do you create I flying bird and I non-flying bird? It's getting messy. But here's the thing, LSP doesn't fail here. Your abstraction does. So what's the solution to this problem? Actually, LSP has no counterexample, so I can't show you any like I did with SRP or OCP. If LSP is observed, it applies. If it's not observed, it doesn't. Maybe you shouldn't have made a bird fly method in the first place. And still, what if penguin is a bird that cannot fly? Who cares? You catch the exception and move on. What LSP actually tries to tell you is if you have a fly method, the bird shouldn't try to drive a race car instead. If it can't fly, well, as if not supported the exception was an anti-pattern. Interface segregation principle. Make fine-grained interfaces that are client-specific. Also, clients shouldn't depend on interfaces they don't use. Sounds logical, but this one contradicts SRP immediately. SRP tells you to keep everything together if it's one responsibility. ISP tells you to break it into tiny interfaces. So, which one do you follow? If you know advanced API design, then you know that yes, every single method is also an interface. But do you also create a named interface for every method to adhere to ISP? Also, how do you know who the clients are when you're designing the interface? If you guess wrong, then you end up with explosion. I this, I that, I maybe this too. Say you're modeling a game engine. A game entity state can be updated, can be drawn, can collide with another object. But if you put it in one interface, it's violating ISP. If you split it, now your collision handler can't even accept a game entity because it only sees iCollidable. And maybe the other object you're colliding with is not an iCollidable itself. So what do? You start duct taping interfaces back together. In real world, oh, this is just a mess. You either have one big contract or 1,000 little shards. There's no perfect answer, but pretending that ISP gives you one is misleading at best. And finally, the dependency inversion principle. Depend on abstractions, not concretions. Straightforward, actually quite related to ISP. You should consume only parts of an object that you use. Now we're getting somewhere. There's actually a design issue with OO that's related. When you expect a dependency in your object, the consumer must provide the dependency of the proper shape. But why is that a problem? Because clients of the class can't fix the issues of libraries. You must provide a certain interface or subclass. No workarounds. If the base has faulty logic, you can't fix it by providing a correct workaround. But let's be clear, this isn't a principle. It's a consequence of language design. If your language supports interfaces and inversion of control, you use it. If not, you find other ways. This example actually combines dependency inversion, where you depend on an abstraction instead of a concretion, and dependency injection, where you state your dependencies explicitly as parameters. The latter allows for looser coupling. On the left, DIP compliant. You inject an email sender. On the right, you knew it directly. Even if you placed it as a parameter and didn't knew it directly, you can't properly swap out the implementation. Guess which one's easier to test, reuse, replace, cache, or mock? Exactly. So yes, DIP helps. But it's not unique to Solid. It's just good software engineering. Languages were designed with this in mind in the first place. Now, let's zoom out. Even if you forgive the flaws in each principle, the whole package of Solid is a problem. First off, the acronym is forced. S wasn't even in the original list. It was bolted on later to make a word, so it's not a philosophy, it's marketing. Second, it's dogma. It teaches people to memorize rules instead of asking, how do I properly solve this problem? It's telling you, this is how you do it, son. These are the principles that you have to follow. Otherwise, you're just maybe a bad person. It doesn't even allow you to question, are there any more of these principles? No. These are it. Not 6, not 7. Certainly not 4, even though originally there were in fact 4. The way it doesn't offer any alternatives or contextualizes the principles should be a red flag if you're knowledgeable in communication techniques. But know this, if you follow Solid to the letter, you'll often end up with worse code, not better. And it ignores trade-offs, complexity, readability, cognitive overhead, performance. We, as a quote-unquote industry, picked Solid as our flag bearer. You remember there were 6 other principles, right? Why didn't we just pick RCC or ASS? There's another thing we don't talk about. Tech has changed a lot. Most developers today don't build frameworks from scratch, they use existing ones, and those already dictate structure. Nobody's designing giant inheritance graphs anymore, and those who do, believe me, don't have Solid posters on their walls. Many problems aren't even solved with OO anymore, and they shouldn't be. And yet we keep teaching Solid like it's universal truth, usually even without proper understanding. Because it's easy to teach, because it sounds deep, because nobody stopped and asked, does this still make sense? Read the paper, read the book, see for yourself. So where does that leave us? Let's be fair. Solid was trying to solve real problems. Code that's hard to change, systems that are brittle, classes that are doing too much. In a way, Solid was not just a simple marketing tool. It popularized coding, the craft, as Uncle Bob calls it. It benefited us all. But we've had decades to see where it falls short. And we're still treating it like it's untouchable. It's time to retire the doctrine. And think for yourselves. Here's my take. SRP is an oversimplification. OCP only helps in very narrow cases and never only by itself. LSP is actually a real principle, the only one with formal roots. Shame there's no real way to apply it to anything. ISP creates mass farther than it solves it. DIP is truly useful, but it predates Solid and stands on its own. Although, credit where it's due, it's popularized by Solid and the nomenclature can be sourced from there. 4 out of the 5 either add complexity or give you rules without real guidance. LSP doesn't, it just exists, is the odd one out. So what's the alternative? Well, the ideas behind Solid are fine. We do want maintainable code, we do want flexibility, clarity, and reuse. But you can't get that by blindly applying rules, at least certainly not these ones. We had ample time to iterate on Solid. You need context, you need trade-offs, you need a brain. So here's what I suggest instead. Think. You start by following Solid, then you understand it. Then you realize maybe you need to break Solid to write better code. And finally, you stop obsessing over Solid entirely and just think. Think isn't an acronym, it's a mindset. Not everything needs OO. Use your language to express intent and constraints, not just behavior. Favor composition. Inheritance is limited. Make your dependencies obvious. Use abstraction only where it actually buys you something, but then do use it. Group and separate code by what it means and where it should live. Don't repeat meaning ever. Design APIs so misuse is impossible. And above all, rules aren't rules. They're tools. Context matters. That's how one should think about Solid, not principles. Guidance. You should understand your tools. And Solid should have been one instead of trying to be the holy book of coding. So, is Solid bad? No. It's just overused, overhyped, and overapplied. It's not evil, it's just not sacred. Take the quote around principles seriously. Solid principles are not proven theses, these are ideas. But the real danger, it gets taught to people before they know how to think critically. They memorize the rules, apply them blindly, and then wonder why their codebase is a mess. What then? Just teach it later. Teach the problems first, let it sink in, then offer Solid as one of many perspectives. Otherwise, I think it's time to retire Solid. It empowers some bad teachers and bad habits and enforces some to teach without proper understanding. So, before I wrap up, I want to leave you with something more valuable than a rulebook. Some hard questions, not answers, just questions. Pause and think about them. Or ask away what I think in the comments or on socials. Because if you take anything from this talk, let it be this. Don't memorize, think. Would Solid have been better if it were based on actual research? Why did these 5 principles go viral and not the others? What even counts as a principle? Where's the bar? Can anyone just say, hey, these are the principles of cheese making? Is Solid just another gatekeeping tool? A badge of being in the club? Why was S added later? And why that one? Why not make another one with an S? Was the real fix to the discount strategy problem? Why is LSP so different to the other 4? Why is it in Solid if it's so different? Did ISP really help you model your game entities better? Is DIP always helpful, or is it just one tool among many? How can it be that DIP predates Solid? If there were a 6th letter in Solid, what would it stand for? And finally, should we even be teaching Solid to beginners? Just some things to think about. That's it, thanks for hearing me out. Whether you agree or disagree, that's beside the point. What matters is whether you paused even for a second and asked, does this really make sense for the code that I write? If yes, then this was worth it. Now go build something that actually works and think while you're at it. Thanks for watching, I hope you liked this video. If you did, then do like it, share it, make it fly, let's make it more viral than Solid ever was. Until next time, and remember, don't ever copy meaning in your code.